Voyager 2 emerged from a time when reaching the outer limits of the solar system seemed nearly unattainable. It was created before modern computing power, before advanced simulations, and before scientists fully understood the risks waiting beyond the planets. Sent on a one-way journey into deep space, it carried the hopes and curiosity of an entire generation. Built using 1970s technology, it runs on memory measured in kilobytes and processing power far below even the simplest devices used today. By current standards, it is remarkably basic. Yet despite these limitations, it continues to travel farther than almost any human-made object ever launched. Year after year, it has crossed every expected boundary, pushing into regions once thought unreachable. It carries the enduring imprint of human engineering, moving steadily through an environment that offers no support for life, communication, or stability. Now separated from Earth by billions of kilometers, it exists in a realm where familiar physical intuition begins to fade. Having passed the outer planets, it has moved beyond the Sun's dominant influence into a region shaped by forces from the wider galaxy. From this distant vantage point, it continues to send back data that is reshaping our understanding of space. At the edge of the Sun's reach lies a boundary known as the helipause, where the solar wind is finally overcome by interstellar space. Beyond this point begins a region governed not by our star, but by the galaxy itself. Scientists once expected this transition to be gradual, imagining a slow fading of solar influence into emptiness. Instead, the spacecraft revealed a sharp and sudden change. Radiation levels rose abruptly rather than gradually. Plasma density increased quickly. The magnetic field shifted direction almost instantly. Rather than stretching over a vast distance, this boundary appeared thin and clearly defined, more like crossing a line than drifting through a transition. This discovery forced a new view of the heliosphere. Instead of a diffuse outer layer, it seems to act more like a structured boundary. Inside it, cosmic radiation is partially deflected by solar activity. Outside it, conditions become far more intense and unpredictable. This has important implications, suggesting that the solar system is enclosed within a protective region. Without it, radiation levels near Earth could be significantly higher, potentially affecting both technology and the conditions necessary for life. The boundary itself is not fixed. Observations confirmed that it expands and contracts depending on the Sun's activity cycle. During periods of high solar activity, the heliosphere grows outward. During quieter phases, it shrinks, allowing more galactic radiation to enter. The spacecraft crossed during a relatively calm period, when the boundary was closer to the Sun, giving scientists a rare chance to observe its dynamic nature. Beyond this boundary, space is far from empty. Instead, it appears active and structured. The spacecraft detected repeating variations in plasma and radiation, almost resembling large-scale cosmic weather patterns. These fluctuations suggest ongoing processes influenced by distant stars, magnetic fields, and energetic events across the galaxy. Another surprising finding involved magnetic fields. Instead of chaotic interactions between solar and interstellar fields, there was partial alignment. This unexpected smoothness raises deeper questions. It could mean the solar system is traveling through a region already shaped by galactic forces, or that the Sun has gradually influenced its surroundings over long periods. Either way, it points to a level of order that had not been anticipated. As the spacecraft continues its journey, it is uncovering more than just distance. It is revealing the nature of a boundary that defines our place in the galaxy. Long after completing its original mission, these signals show that interstellar space is not a silent void, but a place filled with motion and structure. Patterns in particle energy suggest large-scale influences, possibly linked to distant stellar explosions or vast magnetic systems. In 2019, the spacecraft experienced a brief loss of communication. For several hours, it stopped transmitting before unexpectedly recovering. While engineers attributed this to aging hardware, surrounding data showed unusual particle activity and electromagnetic disturbances just before the interruption. Some scientists believe it passed through an energized plasma region, while others suggest the influence of distant shock waves or unknown boundaries. Whatever the cause, it highlighted how little is still understood about this region. Attached to the spacecraft is the Golden Record, a symbolic message from Earth containing sounds, images, music, and greetings. As it travels through interstellar space, this record represents more than communication. It reflects humanity's desire to be known beyond its home planet. Crossing the heliopause marked a major milestone, the moment a human-made object left the Sun's domain and entered the broader galaxy. Each signal it sends back represents not just scientific progress, but proof that human technology can endure in extreme conditions. Despite radiation, cold, and gradual power loss, it continues operating by shutting down non-essential systems to extend its lifespan. Its discoveries are refining our understanding of radiation, magnetic fields, and how stars interact with their environments. These insights could influence future exploration and deepen our understanding of how life might exist elsewhere. Perhaps most importantly, it shows that boundaries in space are real and measurable. The heliosphere is not just a theory, but a protective structure surrounding our solar system. Beyond it lies a region more active and complex than once imagined. As it moves silently farther away, it becomes more than a machine. It serves as a witness to unexplored regions, sending back pieces of a much larger story. Even after its final signal fades, it will continue drifting among the stars, carrying with it a trace of the world that created it. In that sense, it is not just exploring space, but extending humanity's presence into the universe. Even as Voyager 2 continues its outward path, its mission is gradually entering its final phase. Power is limited, generated by a radioisotope thermoelectric generator that weakens year by year. To keep the spacecraft functioning, engineers carefully turn off instruments one at a time, preserving only the most essential systems. This slow reduction is not a failure, but a strategy. Each shutdown buys a little more time, allowing it to keep sending valuable data from a place no other probe has reached. Communication itself has become an extraordinary challenge. Signals traveling at the speed of light take many hours to reach Earth, and by the time they arrive, they are incredibly faint. Massive radio antennas, like those of NASA's Deep Space Network, must listen carefully to detect these whispers from interstellar space. Every message is delayed, fragile, and precious, carrying insights from billions of kilometers away. Out there, the spacecraft is no longer influenced primarily by the Sun, but by the broader environment of the galaxy. Charged particles, magnetic turbulence, and distant cosmic events shape its surroundings. The data suggests that interstellar space is not uniform. Instead, it contains regions with varying density, pressure, and energy, like invisible currents flowing through a vast ocean. These variations may be linked to shock waves from ancient stellar explosions or the movement of matter between stars. Over time, even the spacecraft itself is changing. Exposure to radiation slowly degrades its systems. Tiny impacts from dust traveling at extreme speeds may leave microscopic damage. Temperatures remain extremely low, testing the limits of materials designed decades ago.